Okay, this reaction is near and dear to my heart. I spent a fair amount of my graduate work working on versions of this type of reaction, right? So if you have spent any time thinking about aldol reactions, right, whenever we get an aldol product, we always have an oxygen, and then you have an alpha carbon, and then you have the oxygen on the third carbon over, right? So these are aldol products. If we think about Claisen products, you get an oxygen and whatever is here, right? You get the alpha carbon, and then you have another oxygen on the third carbon away, right? So aldols and Claisens give us 1,3 oxygen products. If we go a little bit further, right, the Michael addition gives us a 1,5, right, where the alpha carbon of the enolate adds to the beta carbon of the conjugated system, and you get a 1,5 product. And so 1,3 oxygen patterns are very easy to make. You use aldol reactions or Claisens. 1,5 oxygen patterns are very easy to make because you can just use conjugate addition and the Michael addition to do that. But in the benzoin condensation, we get a 1,2 oxygenation pattern. And so this is a little bit different and requires kind of a different kind of nucleophile, different kind of reaction. So the first benzoin condensations that were kind of known, well, there's biochemical benzoin condensations, but the first kind of organic chemistry one was sodium cyanide. Cyanide's a great nucleophile. It can add to aldehydes, right? You can get this reaction to go very easily. But what's interesting about cyanide and why cyanide gets its own video in all of this, right, is cyanide is kind of like an amide. You've got extra pi bonds here, you've got a nitrogen there. You could imagine that if you were to remove, or if you, that the alpha position to a nitrile would be acidic in much the same way that, right, that the alpha position of an aldehyde or a ketone is acidic. And so when we add cyanide to aldehydes, we can get a removal of this hydrogen, right? So right now we already have a negative charge on here, and so probably what would happen is you'd have to have some other, um, this would have to pick up a hydrogen from somewhere and neutralize itself to make the cyanohydrin. Oops, yeah, well, that's fine. But now, once you get here, right, we can have something, whether that's an oxygen atom or anything else, right? We can have some base come in, remove this hydrogen, and we can make what's essentially an enolate, right? Removing from the alpha position there, and we get this. And we get an enolate. And this enolate is, of course, reactive at the alpha position in much the same way. So when this comes in contact with another equivalent of benzaldehyde, we can add to that carbon there. And what we get now is something that looks like this, right? So we have two equivalents of benzaldehyde. One equivalent had cyanide added to it and became this kind of cyanide enolate, and the other one just had that enolate add to it. Now, what's really cool about this is, of course, that we can lose cyanide because cyanide is also not only a nucleophile and not only something that can create acidic alpha hydrogens, it's also a leaving group because the cyanide ion is pretty stable. Right? So I'm going to move the H plus around here. Transfer it from one oxygen to the other. And then I'm going to kick out that cyanide to give us the final product, right? This structure with the alpha, the hydroxyl group, the alcohol group attached to the alpha carbon, when those two benzene rings are there, this is called benzoin. That's the name of this structure. And so this gets known as the benzoin condensation, right? So this works because we lose cyanide as a leaving group. So you add cyanide as a nucleophile at the beginning, you lose cyanide as a leaving group at the end. In between, you add H plus here, you lose H plus somewhere, right? We lose H plus in the very next step. And so overall, you have the same molecular formula as two benzaldehyde structures in our final product. No cyanide is added, no hydrogen is added or lost, right? If you count up the carbons, you've got 7 and 7. We've got 14 in the final product. If you count up the hydrogens, you've got 6 on one benzaldehyde, 6 on the other. That's 12. If we add up the hydrogens in the final product, you have 12, 2 oxygens, obviously. And so overall, this compound, like the cyanide, is a true catalyst in that it doesn't, it's not incorporated into the product in any way, but you get this kind of thing. And mostly, this is all, a lot of this comes down to um, this intermediate and this step right here, right? So this base, whether that's another cyanide ion or whatever, removing that hydrogen and making the cyanide into a kind of cyanide enolate, right? That's what allows this reaction to happen. Because what we've done is if we follow this carbonyl carbon all the way through, right? Now all of a sudden our carbonyl carbon is acting as our nucleophile. And so it looks like we just added the carbonyl carbon to another equivalent of aldehyde. But the only reason that works is because cyanide exists and allows us to do this, right? So this reacts as if it's this compound, which of course can't exist, right? But this is essentially the reaction. If you took this and added it to benzaldehyde, you would expect to get benzoin there. And so this is very different from normally we think of carbonyl carbons as the place where nucleophiles add. In this case, the carbonyl carbon is now the nucleophile that's adding to other things. And so this reversal of polarity is referred to by its German name, which is Umpelung, and this is the subject of at least one chapter in my PhD thesis, was the umpalung of carbonyls to convert them into nucleophiles where they wouldn't normally be nucleophiles. So the benzoin condensation is a fun little kind of reversal of our normal reactivity that's dependent on that cyanide ion as the way to generate the kind of the cyanide enolate at that carbonyl carbon.